All right, good afternoon, everyone. Welcome to class. Let me declare up front, I'm not top of the world physically today, but let's see how best we can proceed. For those who had uploaded their mid-session out to the portal, you would have gotten your feedback by now. I'm not going to beat around the bush. I'm not pleased, but I am a little more worried than I would have been under normal circumstances, because many of the errors that I saw resulted from let's say, a lack of appreciation for some of the fundamental principles. Some of the things we may have said or seem to have said in passing, I noted that persons did not take note of them. For example, we talk about, we mentioned in question 1, I believe, that what we're dealing with was a cross-island transmission line, meaning if you're going across the island, then you'll be expecting to be doing so at 138 rather than 69 kV. Little things like that, which goes outside of just a matter of knowing what to do. It is more an appreciation for the theory, really understanding and appreciating the theory. Question 2, the follow-up question. Many persons did that okay. Suffice it to say, there were 1 and 2 errors, which, it's just a matter of persons didn't know what to do, Instead of a series parallel network, they either gave me a series network for the double ground to line fault and that sort of thing. So there's not much we can do about that except for persons to know the theory. Question 3. I was a little disappointed that the majority of individuals who did this particular question seemingly only focused on part 2, which means that, or in other words, seem to have shied away from the theoretical section, where you had to explain yourself. And generally speaking, I think that going forward, well, we only have a couple of weeks left, but in preparation for your final exam, you need to take a different approach. The approach that may have been taken with networks where it's about, knowing some formulae and applying them, you will have to go beyond that, because we're teaching at level 4. And at level 4, there needs to be a little more synthesis in terms of your presentation of responses. And by that I mean it's more than just, giving me back what I had passed on to you in terms of the material, but to really digest it, understand it, and pull from different areas and come up with your final solution or your final response. So your preparation will have to be different. It can't be, a mathematical a mathematical approach. You really have to spend some time going through the theory, and as I said to one person last week, understanding why you're doing what you're doing. That's a level that we're at. Suffice it to say, what I will do at the end of class today, I will upload the full solution set. And for those who did not upload to Schoology, what you will get is just a final mark, because I am unable to provide you with a marked script unless I'm going to print all of those scripts, mark them, and then upload them back to you, which I can't guarantee you I'm going to take on as a task. So you will simply get a final mark, but with the solutions, you can then look to see where you may have fallen down. And then the biggest surprise for me was that at this level, we're now at level 4, you're on the cusp of leaving the university, heading out into the workforce or continuing in the workforce with your degree. I'm shocked that I'm still having to be marking people for and I have no better way to express it, but idiotic rounding off of numbers. Not at this stage, not at level 4. We have warned students about this from Networks 1. And I went as far as to say, especially with power engineering, you don't just glibly round off values, because rounding off something at the, you have an answer 8.0024 as a per unit value, and you decide to round that off to 8. You can't do that. You can't do that. Yes, that's per unit. And you're multiplying that by mega quantities. So it means, therefore, that rounding off, you would have cut off a couple thousands. We just can't do these things. So it was disappointing for me that at this level I'm having to penalize persons for that. No? But I'm going to penalize you, because at this stage I expect that the lesson where that is concerned would have been learned. So forgive me for starting on this with this tone, but it is what it is, and we will, I'm sure, learn from the exercise. All right. So once you have looked at the solutions, then I am more than happy to have a session where we can have further discussions on the mid-session and provide clarification on areas that you wish to have clarified. But for now, we just jump into what's on the agenda for today and continue to look at power system protection. All right. So last week, we spent some time looking at some basic definitions and hopefully trying to get an appreciation for protection as part of the power system. We spoke, the last couple of things we looked at was the whole business of backup protection. And we say that this was dictated primarily by the importance of the circuits or the systems that we are seeking to protect. We also made the point that as being at the core of your power system, that there's significant protection scheme that is applied to your generators. Yes. Now today we're gonna start out by looking at transducers, power system transducers, in particular CTs and VTs, all right, current transformers and voltage transformers. So we just jump straight into that and have a word discussion, and then we look at, in terms of the math or the application side of protection, because we're just doing an introduction to protection. I'll just be looking at how we use the overcurrent relay and how we'd go about setting it. We're not going to be doing any form of coordination, relay coordination. That's for another time. So we'll look at setting your overcurrent relay. But for now, let's talk about your transducer. So why do we need transducers? For your power system transducers, this is about having a convenient way of connecting the measuring or measuring instruments or relays to the power system. Yes? We know that in a power system, and we have been talking about this for a number of weeks now, we're talking about kilovolts, we're talking about kiloamperes. But the reality is we have to be able to measure these. Not only measure, in the case of you know, from a protection standpoint, we also need to know what it is that is happening on the system. What's the magnitude of the currents that are occurring on the system as a result of a fault. So we have just looked at faults. The question you saw that you did the other day, we were talking about several kiloamperes passing through the lines or at the fault point. Now, that current, we need to be able to determine what that magnitude is in order to make decisions. So in the protection system that we have defined, or the protection schema that we have defined, we said that we need to first detect what is happening on the system. And then from detecting it, we process it and then make decisions. So regardless of how high the current is, we need to be able to measure it or to determine what it is. Regardless of what the voltage is on the system, we need to be able to determine it. And so the transducers provide that interconnection. By the way, I've uploaded the figures that we'll be using today. I've already uploaded it to Schoology. I did that earlier. All right. So the key here in terms of your transducers, the key is that they must produce scaled replica. So in other words, whatever is on the system, whatever the current is on the system, and however distorted that current is, we must be able to produce a scaled replica of that distorted current. So the current that is occurring may not necessarily be a sinusoid. It may have deviated from being a sinusoid. We need to be able to replicate that on the system. Not on the system. We need to be able to replicate that for measurement and processing, because that distorted signal also have some benefits. Based on the distortion, we can make decisions as to how to treat with the equipment, whether we remove the equipment from service, whether we allow the equipment to ride out the fault, etc., etc., etc. All right. The performance, as stated here, of our measuring transformers during or after large changes in the input quantity is very important, right? As I said just now, even if it deviates from that perfect sine wave, which is what we would have experienced under normal circumstances, even if it deviates, we still are required to be able to measure it, because during this transient period, certain characteristics can be realized, and it comes back to what you would have done in Networks 1. You would be able to, from these distorted waveforms, be able to determine, for example, some harmonics. And depending on the harmonics that are present, then we'll be able to make certain decisions in terms of the system. Yes? All right. Now, a key point here. We have looked at transients. You looked at transients in Networks 2. You have looked at transients in other modules, yeah? What you need to understand is that because of the magnitude of the currents that are passing through our protection, through our power system, and these currents are usually exacerbated during fault, it may be necessary for us to have the protection system operate in a much shorter time than the transient. Yeah? And so, in order to determine the most suitable hardware in the system, we have to consider what we refer to as the errors that will occur in these transformers. And I'm talking about here your CT and your VT, right? Because these errors can delay the operation of your protection system. And with those large currents, it means that the damage that we were trying to avoid, because remember, your protection system is primarily trying to limit damage and also to reduce outage time, yes? So the point we're making here is that the protection system may be required to operate before the transient dies out. So we have to be able to make the decision during that period where the transient exists. Okay? And to ensure that we are using, as I said before, the best hardware, the most appropriate hardware, we have to consider the errors that exist in our CTs and VTs. I'm not going to go into detail regarding the errors. I'm just letting you know that these errors exist, right? And we have to be cognizant of them. Similarly, errors in terms of our CTs for not only protection, but more so for measuring CTs is also very, very important. Because if you are using your CTs as a means of metering, because hey, you won't necessarily have a meter that can interface with the sort of voltages and currents that we have in the power system. But the fact is, we need to know how much is being supplied. If you recall question number 4 on your mid-sessional, asked you to put together that block diagram. Some person did an excellent job with that, by the way. And you're talking about large customers who may be taking voltages at the same level as your distribution. So it is not like your meter at home, which is interfacing with 240 or 220 volts. We're talking about being able to meter at 24K. Being able to meter at several hundred amperes. Okay. If you then have CTs with errors, with certain levels of errors, then it means that either you or the utility will be robbed of funds or revenue, as the case might be. All right. So the transducers, as I mentioned before, are primarily your CTs and VTs. And I did mention that in all the text, you may see the VT referred to as PT. Same thing we're talking about. All right. For your CT and VT, their primary is connected directly to the power system, and the secondary goes to the relay or other systems that utilize their output. But for now, for the most part, we're talking about relays here. Yes. So the key here is that the output of your CTs is standardized. Right? The output of your VT is also standardized, and I think I mentioned those values last week for your VT. All right, so the standard output for VT is 110 face-to-face, 63.5 volts face-to-neutral. Okay, but the standardized output. So the standard output for your CT would be 5 amperes. That's on the output, but of course, on the input side, that 5 amperes would be based on maybe 1,000 to 5, or 500 to 5, or 1,200 to 5. Yes, or you can have a multi-tap CT, where you have different tap values, but of course the same standard 5 ampere at the output. So it means that for a 1,000 to 5 CT, if I then have a current of 2,000 amperes, I would expect to get 10 amperes on the output. Okay, so you have the standard output, which is 5 amperes. You used to have, and this will be primarily associated with British Standard, a 1 ampere output. So you have 1 or 5. Okay, but for the NEC, ANSI standards, it's a standard 5 ampere output. Okay, so here we have, and I mean, obviously I took this from an older text, but this would be your VT, the voltage transformer. Yes, and here's your CT. So the power conductor passes through the Courier CT, and you have an output. For your power transformer, it's connected directly to your power conductor, and then transformed, and you have your standard output, the value of which I have already indicated. All right, but for your CT, whilst the output is standard at 5, you have different based on the turns ratio on the primary side. Okay. Now, what we have here, these would be your CTs. All right, so your CTs are right here. And what we have, these would be your bus bars. And this is a commercial system. So that's your bus bar, your 3 phases. Of course, you have another CT here. These may, for the most part, be for measuring for revenue purposes. Okay. And so your output from that would then go to your meter. And so the customer would be metered. And I did point out that the gold standard is that once you're dealing with currents above 200 amperes, that you would include or involve the use of current transformers. Right. So as I said earlier, these figures that I'm showing, they're all in the in Schoology. So if you plan to review the video, then you can watch them alongside these figures. All right, and any questions, comments so far? And I've been rambling on from 4 o'clock, but any comment?
Yes, sir. One question. Yes. Could you just explain about the ratio of the CT again, please?
All right. Then I'm going to go to the next slide and deal with the ratios a little more.
Okay.
Okay. All right. So what we have here, this now is the output curves for your CT. All right. So this is with your secondary exciting current. Yes. And over here you have your voltage. Oops. All right. Okay. Over here you have your voltage. Now I'm gonna give you another diagram for your showing your CT. Do I have it here? No, I didn't put it in. But anyway, let me use this to explain it. Mr. Clark just asked about the ratios. So these are the current ratios for your CT. The CT that you're looking at is a multi-tap CT. It's a multi-tap CT. So what you have here, you have, I trust you can all see this line here. Everybody sees that? And there's another area right here. Right? So you have A and you have B. All right. Now, what these two are showing you are what we refer to as the saturation points for your CT. Simply put, at your saturation point, what happens is that as the current increases, the output voltage of the CT will not increase. I'm not going to get into the full definition because I'm trying to keep it, as simple as possible. But you understand the concept of saturation. So you're increasing the current, but the voltage is not increasing. And if you note, from this point up to where the saturation is shown, it's quite linear, right? So you do have a more or less linear increase up to that point. But once you hit saturation, then you start to get the curve, and beyond that, it then flattens. So it means that I'm increasing the current, yes, but in terms of the output voltage, that remains flat, all right? So that is saturation. What's the implication of that? What that tells us is that if, for example, I'm using the 100 to 5 CT, okay? Say I'm using the 100 to 5 CT. It will give me a maximum output voltage. What was this? A C200. Anyway, it will give me, this would be 220 rather, 20 volts. Okay, so let's say that's the maximum output at that point. And this is the corresponding excitation current. Now, what we're saying, if the current in your system, yes, would produce an excitation current beyond the 0.235, okay? Beyond, let's say 0.4, yes? And this is a Lin curve, all right? What did I say? A log curve, yes? So what you would have here is that the excitation current is going to increase by virtue of the magnitude of the current on the system. So you're interfacing with a system. The excitation current is going to be a function of that current that you're measuring. The output voltage, VEF, is also a function of IE. Now, as VEF, which is what you're measuring, increases, it is also giving you an idea as to what the current on the system is. So if you then exceed that current, but you are not seeing, so you exceed that current, I should have gone horizontally. If you exceed that current, yes, but you are not seeing a corresponding increase in voltage, then it means that you would not be accurately reflecting the current that is on the system. Do you understand that? Let me put some numbers to this. Let us say you are measuring, let's say you are measuring currents of 500 amperes, yes? It would mean that when the CT is measuring that 500, because we have a 100 to 5 CT, it means that the output current would have been 25 amperes, okay? And that 25 amperes would correspond to a particular value of VEF. All right? Now, if the current then goes to 10,000, and that 10,000 amperes would, of course, mean that the output current on the primary would be 500. Yes? With 500 amperes. It means that IE would have shot up significantly. However, the VEF would have saturated, meaning it would not have gone beyond 30 volts. But that 30 volts is maybe would correspond to a current which is much less than 10,000. So the CT would be sending information to the relay, telling it that, the current on the system at present is, maybe 2,000 amperes, or, yeah, when in fact the current is actually 10,000. Yeah, it means therefore that the relay would have received inaccurate information and would not act in a manner that is required to protect us against 10,000 amperes. It would act in a manner to protect us against 2,000. Which is why we said earlier, your transducers need to produce an accurate replica of what is on the system. So it must be able to tell what is on the system. So in looking now at the turns ratio, if you know that you're going to be talking about currents in the region of 10,000, you may not wish to then use the 100 to 5 tap. You may want to use the 1200 to 5 tap, because the output current on the CT side, yes, the output current on the CT side at 1200 will be 5. But when it gets up to 10,000, the output current will be 30. Yes? And that may not drive the CT into saturation. So, as I said, this is a multi-tap CT. A couple of things we need to note in terms of the output curves. It tells us what the ratio is. But for each ratio, it also tells us what the secondary resistance of the CT is. So it gives you the secondary resistance, which obviously, as you see, it is not linear. Yes, it's not linear. But for the 100 to 5, you have 0.05. For the 200 to 5, you have 0.1, etc. Now, all that is happening there is because we are using different taps on the secondary. It means that the amount of wire, and by extension, the resistance at the secondary will change or will be different. So we're just tapping off different points on the CT. So this would be classified as a 1200 to 5 CT or 1200 to 5 multi-tap CT. Okay. So for as an introduction to the whole protection thing, what I want you to be focusing on is the fact that your CT has different taps. We won't need to consider the resistance just now. Yes. We also need to note that, yes, your CT can saturate, and beyond saturation, it's going to give you inaccurate outputs. All right. I don't know if that answers your question, Mr. Marcel. Mr. Marcel.
Yes, yes.
Good. Okay. So the other part of the system, we just spoke about the transducer. So we know we have a CTs, we have a VTs. We also now need to talk about the relays, right? And relays, as we mentioned before, can be used to measure or to process different bits of information. What we have before us, these numbers tells us the type of relay that we are dealing with. So if we're going to delve into protection, you would have to, familiarize yourself with these relay numbers. What does 50 represent? Is that an overcurrent? Is that a distance? Then you have your 21, again, that's distance or over, which is it? You have to know that. You have your 87. So these numbers that you'll see here, will tell you the type of relay that is being used on the system. These coils that are shown there, those are your CTs. That's what's interfacing with the power system. And then the output of those CTs go to your relays, and your relays are the decision makers in the system. All right. So a whole slew again of relays in terms of relay numbers are shown. So, you know, what is your 87? What is your 86? What's your 25? What's your 21P? Or, you know, what is 21P versus 21? You know, so these are all your relays, or relays that can be part of your protection system. What we're showing here, if you note, this would be a CT, yes? But here, this would be a VT, right? So that's your voltage transformer. So there are some relays, depending on what we're doing, that needs multiple outputs. Did I say multiple outputs? No, multiple inputs. So these relays require both voltage and current. All right, so you have some relays that require both voltage and current in order to make their decisions. There are some relays, and that's the one that we're going to spend a little time looking at, that requires only current input. So we need to know, we need to get output from CTs for those relays. But there are others which requires both CTs and VTs. Okay. Now, by way of definition, you know, we need to be a little more scientific, so to speak. Maybe not the right word, but anyway, we need to give a proper definition for a relay. What's a relay? Yeah? Relays are all around us, you know. These days, you know, back in the day, it was okay to go inside your motor vehicle and mess around a bit. Today, I open the bonnet and I just close it immediately because, you know, you don't know what you're touching sometimes. But anyway, relays are all around us, you know, vehicles, control systems, you know, you name it. So what we talk about when we talk about the relay? Key here, students, the key here, it produces a certain predetermined change in one or more electrical output circuits, right? So the relay, as I said, the decision maker, what it does, it gets inputs, and based on those inputs, it then it takes certain action that would have been pre-established. So it's predetermined. So it says if the current is X and the voltage is Y, this is what I do. If the current is above X, this is what I do. If the current is below Y, this is what I do. All right? So it makes sudden predetermined changes in output circuits when certain conditions are fulfilled in the input circuits controlling the device. All right? So it takes the current from the CT. Based on the current that the CT provides, it operates. Then you have another relay that's not just looking at the magnitude of the current, but it's looking, or it's trying to decide from what harmonics are in the current. So those decisions needs to be made, right? Yes, Mr. Grant. So Grant?
In regards to the relay circuit, you said something just a second ago, well, a few moments ago, something about distance and how as it relates to protection. But I totally lost the question because I was fascinated with what you said a second ago. All right, so now when you speak about the relay, sir, could you shed a little bit of light as it pertaining, because we're talking about protection, could you shed a little bit of light in terms of how relays would work in sequence or the sequence currents?
All right. Now, for me to, what you mean the sequence currents that we dealt with in terms of fault analysis?
Yes, in terms of the unbalanced faults, sir.
Okay.
Generated.
Okay. No, all right. Now, let us first be clear about something. When we looked at those sequence networks, etc., that was a means to an end. In other words, what we're trying to determine was the fault currents and voltages in the system. That's what we're trying to determine. So, in the sense of relays, even though yes, relays do detect like zero sequence currents, which is really earth fault currents, right? But I don't want to confuse it with that. Consider the sequence currents that we calculated or we used as a means to finding the fault current in a line or the voltage during a fault. So let's be clear with that. So if you go back to the exam, you know what I asked you for the fault current, and that's where a lot of persons lost a few marks, because a couple of persons just went ahead and found the per unit currents or found the sequence currents. That's not what we were interested in. That's a mathematical technique in order to get I, A, B, and C. Your relay now, what it's looking at is the current in phase A, the current in phase B, the current in phase C. Yes? So your CTs, and it all depends again on the level of protection that is applied. CTs will be monitoring each of the phases, and the output of each phase would then come to your relay. Now, again, it depends on the type of relay that we're dealing with. So if it may be an overcurrent relay, all the relay would be looking for is that the current, if it exceeds a certain value. So if the current exceeds, I'm trying to say it without getting into the details, but if it exceeds 5 times what it's supposed to be, then the relay will trip. That's the overcurrent relay. But another relay looks at both voltage and current. And what it does is that it looks at the ratio of the voltage to the current. And if the ratio of the voltage to the current is too small, it trips because it says that the impedance is too small. That again is another type of relay. That's what we call an impedance relay. Yes? You have relays that are going to use differentiators, or it's going to have some signal mixing, and depending on how the signals are mixed and what the output is, it's going to make a determination that yes, there's a fault in the system. I need to trip. So we could go through a plethora of relays. Yes. But the fundamental principle remains, which is it has predetermined actions based on specific inputs. So it's going to give you an output based on what the input is. All right? Focusing more on a protection relay. Right? Remember we said at the beginning of this section that in terms of the action that is initiated, it can either request disconnection. So it may request the circuit breaker to operate. So that's one possible action, but it also can send an alarm. Good. So the relay will initiate disconnection of a part or the entire installation. Yes. Or it may operate a warning signal, which is then sent to system control or, you know, just sent to an audio alarm in the space. All right. But again, just keep in mind at this stage, Mr. Grant, just keep in mind that the relay is simply there to operate in a particular way based on the input that it receives. And once it receives that input, it's going to operate. Okay?
So therefore, a relay is a transducer then?
No. Remember, the transducer is doing some conversion. So it's moving a signal from one state or to another. The relay is a decision maker. So it receives and makes a decision.
Okay.
So it's not converting the signal. It's not doing anything special to the signal rather than interpreting the signal and acting on it. All right? So we have here two different types of relays. We have the static relay and we have the electromechanical. All right? And, you know, I'm sure you're all old enough. You would have seen the watt-hour meters that have that dial that turns. Yes, the principle on which that watt-hour meter is built was used or has been used for relays, and I will dare say that even to today, you know, because these relays are so robust, even though you have one or two of them still being used in the system, right? One or two. But primarily, I mean, you know, we may not know it or we may not be very familiar with the fact, but, you know, our utility company is among the most modern around town, you know. Within the Caribbean, you know, we are leaps and bounds beyond many of our neighbors. So too our communication network. I believe the Caribbean, you know, they're catching up a bit with telecom, but, you know, we are certainly ahead of the pack in many respects with the utility company. So primarily you're going to see your static relays, right, which use microprocessors as part of its makeup, as against the electromechanical. All right. So in terms of the technology, therefore, that we are talking about, you would have for your electromechanical, you have attracted armature, moving coil, induction, thermal motor. These are the relaying elements in your electromechanical. All right. So the outputs, you know, based on the input, the output may cause a physical movement of an arm, yes, within the relay. It may cause the circular motion of a disc, just like in the watt-hour meter. What you had were two currents being superimposed on that disc by way of magnetic forces, which then caused the disc to turn. And of course, for those who, yeah, you're all old enough, I'm sure. If you took note of the the electromechanical watt-hour meter, as you increase the load inside the house, you'd see the disk going much faster. Maybe that is part of what is affecting many persons today, because they no longer see that disk, you know, turning as if it's trying to cool down the house. You know, they may not recognize that they're using as much electrical energy. You know, you only come out now and again and see the digital output. But the same principle is true for your protection relay. Meaning, the higher the current, the faster the disk will turn, and the faster it will move a movable contact to a fixed contact. So it means that it will trip faster with a higher current. Same principle. This is your attracted armature. Yes. Here you would have the input. So you'd have your input here for your relay. Okay. And based on the current that passes through that, then it would have a magnetic output or magnetic impact or effect at that point, yes, which would then pull the armature forward, thereby moving the contacts that we have up top. Yes, and you see we have two contacts there. We have a normally open and a normally closed, which are defined in their de-energized state. Right, so your normally closed is closed when de-energized, and the normally open when de-energized. All right, and so with what we have here, when that armature is attracted, it would then close that gap and then move the movable contact from one point to the other. So again, based on the principle, and that is what I want you to focus on, because, you know, when we get to talking, you know, more deeply with respect to protection, then we look, you know, at the different technologies or more deeply into the various technologies. But for now, it's the principle that I want you to appreciate. Once the current coming in, yes, is at a prescribed value or beyond a prescribed value, then the armature would move and the decision will be made based on the contact. If the current isn't strong enough, then it means that this would not move high enough. So therefore, the contacts would remain in place. If the current goes beyond a certain value, then it will move much stronger or much faster, and we would then close our contacts and open the contact at the bottom. All right? And that's what we mean by predetermined. So there's no if, but, or maybe. Current at particular value, armature moves and makes the necessary connection. The next figure isn't very clear, but I'll present it nonetheless. Again, what you have there, you have two magnetic fields. You have one that is being produced by the input current, and that is why we are able to measure power with meters like this. You have one current, one magnetic field that is being produced from the current that is being consumed. And then there's another magnetic field that is based on the voltage. So it's the voltage will produce a current, right? That would result in that magnetic field. Both fields are superimposed on the rotating disk. And of course, you know, you go into details with this in terms of the the braking magnet, which, you know, you hear a person say, well, you know, their meter was turning so fast, and when they turn off everything, the meter don't stop immediately. Not exactly true. But, you know, there's some logic to it. There's some logic to it. But for the most part, it's not really an issue, because you have to recognize and accept that you know, you do have some momentum issues. So there's momentum in terms of stopping, and there's not momentum, inertia in terms of stopping and inertia when you start up. So you win and you lose, and it balances itself out. All right. So this is what I know the internal parts of our electromechanical meter would look like. Of course, I am still keeping my fingers crossed that, you know, we will be back face to face come January. And so you'll be able to, if you're doing protection, you'll be able to touch and feel these meters in the lab. We also got a gift recently, really appreciative of it, of some more modern meters, relays rather. Yes, Mr. Wilby.
Just confirm. You hear me, sir?
Yeah, man, go ahead.
Just confirming, you said that we'll be going back to face come January.
No, I'm saying I'm keeping my fingers crossed.
Oh, okay.
Yeah, I confirm that. That's above my pay grade.
All right, sir.
All right. So again, the figure before you, very, very, very poor, but I have put in some, I've written in some things there just to help us recognize what would be incorporated in an actual relay. At the top, what we have is what we refer to as a plug block. And this plug block, you can see these holes, right? These are holes. These are all holes. And what we have right here, this thing sticking out, that's the plug. So the plug block have these holes, and at the top of each plug block, you would have a number, right? So this is the relay that we're going to spend a little time trying to understand its operation, right? Some of its operation, right? So you have these holes, yes? And at the top or written beside each hole, you have a number. And that number represents a current value, right? Now, if you want to change the current at which the relay will operate, because remember we said earlier, your relay takes in certain inputs and then makes takes predetermined action. Good? If you want to change the current at which the relay will operate, we would simply remove this plug and place it in one of the other holes. And that hole will determine what we refer to as the plug setting for your relay. The other term that we use for plug setting is tap setting, because as you can see, that plug block, all it is doing is that the windings through which current will flow is tapped off along this plug block. So it means that, well, you know, this may be 1 amp, this may be 2, this may be 4, this may be 6, 8, and this may be 12. So if you want the relay to operate at lower currents, then you'll put it in one of the holes to the left. All right? And vice versa. So the plug block, or the plug block is where you make the selection for the operating current. The plug setting is the current that you would have selected. And the tap setting is the same thing. So I give you three things there. Plug block, plug setting, tap setting. All right, now, down here, again, not very clear, but it is what we know, what we refer to as a time dial. All right, time dial. Now, when you access the pictures, bring it up on your computer and expand it a bit, and it may be a little clearer. At the base of the time dial, let me get rid of this ink. At the base of the time dial, right here, can you see that? Well, I'll mark it up now. It's right here. Let me outline it. All right. That is a fixed contact. So I'm sorry. That's your fixed contact. No. My apologies. That's your movable contact, and it is fixed to the disc, which is here. All right. Now, your time dial. Let me explain this quickly and make sure I get this accurate. Your time dial carries your fixed contact. Now, why do we call it time dial? Your movable contact will rotate or move based on the rotation of the disc. So your disc, remember a couple of things we said about the disc from your old watt-hour meter. The first thing is that it will move once current is passing through it. Good? For your protection relay, the disc will move if and only if the current exceeds what you have selected as your tap. So your tap tells the relay at what current it should operate. Good? Now, the higher the current will be the faster the disc will rotate. Now, your time dial setting will adjust the distance between the movable and the fixed contact. So if I use a short time dial, if I use a shorter time dial setting or a smaller time dial setting, what it means is that I have moved the fixed contact closer to the movable contact. So when the disc rotates, what that means is that it will get to the fixed contact much faster. So by increasing my time dial setting, I'm increasing the time of operation because I am increasing the distance between the movable and the fixed contact. But again, the figure is not very good. Well, I just really need to go find a better one, right? That's my response. But anyway, when we get into the lab, you can see this, right? We'll show you this again. All right, so that's it for the electromechanical. But of course, we have our static relays, and these are some of the relaying elements that are used, right? For that relay. You have your magnetic amplifier, thermionic systems, your semiconductors, your photoelectric, and your microprocessors. Quite frankly, most of these, given where we are, we can strike them off the list. And we are primarily down to microprocessors. All right? Even though, the photoelectric does have its years of application. All right? And this is what your microprocessor, well, you all know what that looks like. All right, this is a board coming out of one of the relays with the various microprocessors on the board. Okay. So your protection relays, your protective relays, and we have been mentioning this before. We'll just zero in back on it. Your protective relays, it look at power system quantities, we know voltage and current, yeah? Power, impedance. So we know that in terms of a power relay, it will be looking at the product of your voltage and current, right? For your impedance, we're looking at the ratio, yes. And so the ratio. How do I use magnetics to deal with that? You know, again, I hope I'm piquing your interest. But the impedance relay use what we know as a balance beam technology, yes. And for your power, that's superimposing two magnetic fields proportional to V and I. All right. So your relays in protection, these are some of the quantities that we look at. You have frequency relays, but they're not really measuring frequency, they measure voltage. And the voltage is a function of the frequency, or the frequency a function of the voltage, depending on how you want to look at it. All right. So we have magnitude measurement relays. And a magnitude measurement relay is going to respond to the magnitude of the current or the voltage. Yes? Here we're talking about the frequency relay, right? So it's calibrated in frequency, but what it's actually measuring is voltage. Yes? And we've been talking about the overcurrent relay, and that's the one that we're going to spend a little time in terms of you know, looking at the math associated with its operation. We've talked about this. The induction relay, you know, we're looking at interaction rather of two magnetic fields, yes. Same principle as with the watt-hour meter, yes. And those are superimposed on your disk, which determine operation, all right. And well, I was gonna say you would have looked at something like this in instrumentation, but the truth is I don't know what the instrumentation syllabus looks like these days. I haven't looked at it in a while. Okay. And this is what we had shown earlier in terms of the watt-hour meter principle. Okay. So this is your product measurement relay, where the overall torque is given by K phi1, phi2 sine alpha, where alpha is the angle between the fluxes, and phi1, phi2 are the interacting fluxes. I've been doing well so far, but sorry about that. Okay. Time is 10 minutes after. All right. when you're doing AC, not necessarily in networks, but maybe in physics, yes, you know that we can combine quantities once they're operating at the same frequency. But, well, I shouldn't even go to a subject like physics. The whole principle of phasors, you know, we use phasors. The whole principle is based on the fact that we are using quantities of the same frequency. That's a principle under which we can use phasors. So if we're able to have these fluxes, same frequency, we have them superimposed, we can find a product. So whatever quantities that we want to measure or make a determination, you know, based on their values, we use our product measurement relays. Yes. We also have ratio measurement relays. We can have, as I was saying earlier, for your impedance relay, you're looking at the ratio. Yes. But we can have a balanced beam. Yeah. Where you have one force FA, unstable internet. Let's keep our fingers crossed. But anyway, you have FA being equal to K1IA, and you have FB equal to K2IB. It's K and K1 and K2 just constants, but we're saying that those are dependent or constants based on well, let's keep them as constants of proportionality. I'm really trying to keep on the outskirts here with much of this. All right. So for a balanced beam, what we are saying is that when you have balance, then that is true. All right. And the departure from that balance will cause operation. So remember when we spoke about the impedance relay, the impedance will be looking at V over I. Yes? And if I increases, then, well, V over I we know is equal to Z. If I increases, then Z falls. All right? And so the impedance relay operates on this principle. All right? So if the impedance measured on the line is less than the predetermined value of impedance, Z, then the relay is going to operate. All right? So what we are saying here is that we have the established ratio, and once this changes, or once this balance changes, which is going to change because you have a fault on the line. If you have a fault on the line, it means that the current is going to increase. As a matter of fact, usually when you have a fault on the line, the current will increase and the voltage will collapse. So you'll have a smaller voltage and an increase in current, which means obviously that the impedance is going to fall. If the impedance falls below the predetermined or the preset value, then it will cause the relay to operate. Okay? There's a little more to it, but that's all we need to consider for now.
Sir.
Yes, Mr. Freighter.
Here's the same thing you were saying earlier, that the voltage remains constant while current increases.
Well, you mean when I was talking about this?
Yes.
Yeah, what I'm saying, all right, the voltage during a fault usually collapses, usually gets smaller, yes? But what is true, what is absolutely true is that I will increase significantly. So even if I said that V remains constant, which I know it doesn't, right? It usually falls. And you would have seen that in the exercise that I gave you, the test I gave you the other day. It went to 50 odd kilovolts, all right? So you usually have a slight collapse in your voltage. But with the significant increase in current, yes, Z will fall. And once Z falls, then the established balance that the relay was set for will be disturbed. And once that is disturbed, then it will operate. As I said before also, there's a lot more to it than what I'm saying. Yes, but I don't want to, take persons off the beaten track unnecessarily. All right. So as I said before, the one that we're going to spend a little more time on is your overcurrent relay. Yes. So the output of your CT goes to your overcurrent relay. And if the magnitude of the current is greater than the predetermined pickup current, when we talk about the tap current, and we said that it was also equal to the plug setting, that's the same current we're talking about. So how many names have I given it so far? 3. So if I talk about the pickup current, if I talk about the plug setting, if I talk about the tap setting, I am talking about the same thing. Let me go again. Plug, tap, pickup. All right. So that pickup current, yes, which is the operating current for your relay, once it is exceeded, the relay will operate. Your overcurrent relay, however, its operation, the speed of its operation will also be determined by the magnitude of the current that is received. And that magnitude of current is related to what we call multiples of tap. So it's not just how large it is by how much larger than the tap current it is. Don't worry, we'll come back to it. So much things you have to come back to, but we'll get there. Don't worry, don't worry. Have you ever given me a reason to worry? Not at all. All right. So for your overcurrent relay, this is the setting. All right. So this is my power system. This is my CT. And those dots there are just polarity markers for your CT. All right. Once I prime. Now I prime. What is I prime? I prime is the output current from the CT. And that current passes through the operating coil of the relay. Yes? Now, a couple of things we need to note. When that if that operating coil is energized, meaning the I prime exceeds your tap current or your pickup current, yes? It will then either close this. Well, it exceeds it, so it will close it. If it closes it, then immediately, all right, so we had a normally contact there. Once it closes, then it will energize the breaker trip coil. So the relay itself does not carry the system current or the fault current. Yes, it then energizes the trip coil for the breaker, and the breaker then opens the circuit up here. Okay? Again, you have the figure. You can go through it a little more detail. Sorry about that. Don't worry, it's my sinuses. Genuinely sinuses. Nothing else. At least I hope so. All right. Yes, Mr. Gray?
No, I was going to say okay, but it's okay, sir.
Don't worry, we're not sharing AC today. Don't worry. All right. So in terms of the operating characteristics for your overcurrent relay, what we're saying, once the current is below the pickup current, then it will be blocked. So in this region, current is blocked. Once it goes above IP, then the relay will operate. Yes? But of course, I also said that the magnitude of the current will also dictate how fast, the relay will operate. So we have to look at, how time is tied into the whole operation of OCT. So we have your time delay overcurrent relay responds to the current magnitude, but with an intentional time delay, right? And that time is depending on the magnitude of the relay input current. Now we said that. Now, write this, please, and make sure you underline it. Note what we're talking about. What we're talking about here, students, multiples of pickup current. So if we have large multiples of pickup current, the relay will operate quickly. So the relay, the speed of operation will be dependent on the magnitude of the current based on multiples of pickup. So if my pickup current is 5 amperes, and the output from my CT is 15 amperes, then the multiple of pickup would be 3. So the relay would not be operating, so to speak, based on 15, but it will be operating based on 3, which is the multiple of pickup. And we'll show that when we look at the output curve for our relay. All right? Has anyone accessed the figures from Schoology? Anybody access it? No? Okay.
What figures, sir?
Sir, I was looking, but I'm not seeing them.
You're not seeing them? They're in the first folder with, what's that folder? That folder that I have the schedule in.
Oh, okay.
Yes, sir, seeing them.
Yes, you have access them.
Okay, good. So we're looking at the multiples of pickup, and that is very important. It's not just the magnitude, but the multiples of the pickup current. All right. So what we have here, what we are showing is that as the current increases, yes, then the time delay, so these are the time delays that we have on the system, yes, is reduced. So the larger the current, the faster it will operate. So TD1, which is all the way out here, yes, would be a shorter time than TD2. Similarly, TD3. All right. And we will have to, if you have a number of these relays in your system, you would have to find a way of what we refer to as coordinating these relays to ensure that, you remember we spoke last week about things like discrimination and selectivity? That's what coordination would provide in your protection system. All right, so for your overcurrent, you have this time delay, yes? And that time delay will be based on the multiples of top. The larger the multiple of top, the shorter time it will take for the relay to operate. So I come back to that poor figure that I have been using. Yes. I'll come back to that slide in a minute. But this time dial here, that's what I would adjust depending on how fast I want my relay to operate. Okay. So the characteristic curves of your overcurrent relay is a plot of the operating time, yes, against the relay input in multiples of tap. Very, very, very important. Multiples of tap. So you have the pickup current, which is the same thing we say about, we call it tap current or plug setting, yes? So we have the pickup current, and then we have the time dial setting. So for your overcurrent relay, very important, for your overcurrent relay, 2 settings we will need. All right, so you need 2 settings for your overcurrent relay. No matter how complex the network is, you only need 2 settings for this type of relay. The first is your current setting. And that current setting would be your pickup current, which tells the current at which the relay will operate. And the second setting is your time setting, which would be set by your time dial. Of course, you don't have these physically, you won't be interacting with these physically anymore. You'll be putting these, you'll be uploading this information from your laptop into your overcurrent relays, because we're dealing with static relays in today's day and age. All right, but for me to understand the principle, yes, to understand the principles, nothing better than the electromechanical. So I go back there, but I'm also saying to you that whatever we're doing with the electromechanical, it is simply uploaded to your static. So the time dial setting, yes, you'll be adjusting this. So that's your time dial. And for your plug setting, you'll be adjusting that. So those are the 2 settings you need for your relay. All right. So let's look at the curves. Any questions, any concerns so far? I know you have concerns, but any questions? No? All right. For your characteristic curves, all right, there's some inverse proportionality between the current and the time, which we expect. Higher the current, lower the time. We have been saying that. So let's look at the operating curves. This is what your curves look like. All right, so this is from your overcurrent relay. So let's talk now about what we have before us. First things first. On the right-hand side, on the right of our curve, well, not the curves, but anyway, on the right-hand side, we have here the tap settings. So these are the available taps on this relay. So the type of the relay is up here. It's a CO8 overcurrent relay, right? Can be used on 50 or 60 hertz systems. And what we are saying, these are the tap settings. So based on the circuit that you would be protecting using this overcurrent, you will first have to determine what current setting would be required. All right, we're gonna go through a little exercise that will help you with that. So what are the 2 settings we need? The time setting, tap setting. So over here, you would select the tap.
Excuse me, sir.
Yes, Mr. Gray.
You have numbers on the right side, right? Is it that?
You're not seeing them?
Yeah.
They have 0.5, 0.6, and it goes all the way up to 12.
Yeah. And those like each line is for them. Yeah.
We're okay with that?
No, I'm saying is it 0.51 would represent the numbers on the right side?
I'm not hearing you clearly. You're asking if there are numbers over here on the right?
No, the numbers on the right side, right?
Uh-huh.
Are they representing the same numbers in the graph? 0.5, 1, 2,
No,
3,
no, no,
4,
no, no,
8,
no,
5.
no, 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 man. We don't reach this here. Just focus on the ones on the right. On the right, you have the top settings. So these are what you would use to determine the current at which the relay will operate. All right?
Okay, all right.
Good.
All right, sir.
We'll put a full stop there. Next, remember we said we need two settings. The next setting we need would be the time setting, and that is where these come in. So these represent your time dial setting. Now, if you go back to my diagram, I don't know, well, you can't see the numbers, but if you look at the top here, if you look at the top, you'd see these are where the numbers are. Okay, can you see that there are marks there? You can't make out the numbers, but can you see the marks?
Yes, sir.
Yes, sir.
Yes, sir. So those marks that you see at the top, that's these values there. So you'll be selecting one of these 12 values, 0.5 up to 11. Those are your time dial settings. And remember what I said, the smaller the time dial setting, it means that your relay will operate fastest. Now, having shown all of that, we now look on the axes. So on the y-axis, you have the operating time in seconds. And on the x-axis, you have multiples of tap. Now, I can try and explain all of this, but I guarantee you that it won't work. So what I'm going to do is to, Okay, what I'm going to do is to ask you just to take this question, and then we'll go back to all right. So the secondary current of a CT connected to an overcurrent relay is 5, 10, 24, 120. Using the CO8 characteristics, estimate the operating time of the relay if the top setting is 8 and the time dial setting of 1 are used. All right, so let me make sure I remember them. 5, 10, 24, 120, and it is 8, 1. Okay, so let's go back to curves. Huh? All right, now let's see to get a volunteer. So I can volunteer somebody. No volunteers? Mr. Will be your hand still up?
No, sir, I never took it down.
That's volunteering. All right, good. So just stay, man. So if we're dealing with part A, Mr. Wilby, at 5 amperes, and we're using the time dial 1, I want you to estimate how long it would take for the relay to operate. Are you able to see the curves properly?
Sir, I am here, sir, but I'm not really. I didn't get to do the questions because I just stepped back in the office.
So I play Russian roulette, Mr. Wilby, with my class.
No, sir, not voluntarily, sir.
All right, can we have a volunteer? What's the operating time for the relay? Come on, folks, we have a few minutes left, you know.
About 0.3 seconds, sir.
Huh?
About 0.3 seconds.
Or 0.3. All right. Anybody disagree with Mr. Mason?
Say close, 0.3, 0.4.
0.3, 0.4. More somebody who can disagree with both of them. I want somebody to disagree.
Sir,
Yes, Miss Gray. Thanks. So what would be the operating time, Miss Gray?
sir, the relay won't operate because the current is lower than it stops it.
Thank you very much, Miss Gray. The relay would never operate because the top current is 8 amperes. And we asked what would be the operating time at 5. And so the relay would not have operated because it has not yet reached the operating current. Okay, Mr. Mason, now Mr.
Say that, sir. I
Mr.
stand
Hope.
corrected.
Yes, sir. Sir, 1 minute. I know it was supposed to be the 8 amperes, sir, but I was actually thinking you were going to teach us how to read the time dial and the 5 amps.
You're waiting for me to teach you how to read a graph, Mr. Mason, is that what you said?
No, not teach a graph, sir. You understand? Because I had some problems last year.
Yeah, but hold on. What I'm saying, the current is 5 amperes. You agree with that part?
Yes, sir. Yes, sir.
What is the top setting?
Top setting is what?
It's right here, so.
8.
What do you mean by top setting?
You were referring that as the top settings, and I think there's 2 other names.
No, I never ask you the name. I ask you what we mean. Remember what I said at the start of the class? We have to go beyond just the basics. So I'm asking you, what does it mean? What is that? What we mean by top setting?
The top settings would be the operational current.
Good. And how does the overcurrent relay operate?
It operates based on the condition of the input.
Okay, so what is the input from the CT?
Which would be 5 amps, sir.
5. Does it reach operating current yet?
None of the above, sir.
Exactly. What do you mean none of the above? It's no.
Yes, sir. Yes, sir.
Yeah, so we're not good, man. It will never operate.
Yes, sir.
Oh, since you say yes, when it reached 10 amperes, what would be the operating time? Look at the curve.
All right, so 10. So to the 10.
What's the first thing you would do? Just tell me what you would do. Just tell me. Don't sit there and try to figure out. Just tell me what you would do.
First, the input, you check the input in which you have a 10 amps. That
all right.
With the requirements.
So you know that 10 amps would cause it to operate, all right?
Yes, sir.
Okay. So how then do you determine how fast it will operate? What do you need to look at?
I would have to look on the relay, which is with the multiple tap. That's the input current, sorry, of multiple of current tap settings.
Multiples of current tap, okay. So you find that.
All right, so based on the input that they gave us 10.
Yeah.
Well, yeah, sorry. The question states that we should use 10 amperes. So we'd look for the 10 on the graph.
No, you just said it. Multiples. What is the top?
Sorry, which is 8, sorry.
So how do you find multiples of top?
We'd look on the graph.
No, Mr. Mason. What is the input current that we are looking at right now?
10 amps, sir.
10. So if the top is 8, how do you find the multiplier, the multiples of top?
would go to the speed dial settings.
All right,
Or the-
all right, all right, all right. Anybody?
Yeah.
If we have the tap as 8 and the current that we have, the actual current is 10, how do we find multiples of tap? How many multiples of the tap? Come on, man, don't talk to me,
Sir,
man.
divide 10 by 8.
10 over 8. 10 over 8 multiples, Mr. Mason. What is 10 over 8? Mr. Mason. Where am I going? Mason? Has he gone? Or is me gone?
Oh, sorry about it, sir. I was
Still here, man.
Go ahead, sir.
So what is 10 over 8?
1.25.
1.25. No, go down here, so Mr. Mason.
Mm-hmm.
Where would 1.25 be located? Just tell me and I mark it for you.
That's directly after the center mark. That's one point. No, well,
This would represent what, Mr. Mason, right here, sir.
that would be 1.5.
Okay, so we're 1.25.
With the height.
A little lower than the spot in the middle.
Hi, Miguel.
Yeah.
It's not really in the middle. It will be a little less, but you know,
Yeah.
guys, it's not a linear scale.
Mhm.
So now, Mr. Mason, it's 1.25. What is the time dial setting that we're using?
8.
Time dial setting, Mr. Mason.
Sorry, 10.
No, sir.
No, you-
Time
you
dial
said-
setting.
You said 1.
1. Now, based on the curves, which curve is that, Mr. Mason? Going from bottom.
Which is 1?
Going from bottom, which curve is it? First, second, fifth, 20th, which one?
The second?
The second one. So how will I now determine the time? Remember, it's a graph. How would I now determine the time?
All right, so we'd use what? The 1.25
Uh-huh.
to match up to the time dial settings.
So just tell me how I go, vertically, horizontally, how I do?
You go at horizontally.
Vertically.
Vertically, sorry about that.
So yes, yeah, I'm hungrier than I am.
Yeah, sorry about that, sir.
So we go straight up, Mr. Mason.
Yes, sir.
Yeah. Does it intersect with the one?
No,
The
sir.
time dial one?
No, sir.
So if I ask you for the answer, what would you say? What answer would you give me?
Infinite.
It can't be infinite. It cannot be infinite, you know.
It would be out of the operating.
All you know, it is greater than 7 seconds. That's all you know. It's greater than 7
Based on
seconds because you really don't know what is happening above that. You don't know where this curve finally will intersect. It's not infinity, that's for sure. Do you understand that, Mr. Mason?
Yes, sir.
You sure?
Not quite, but I'm
All right. We have something else that I want to do, so let us use it the last 12 minutes. The next one is 24. Since Mr. Hope was helping him, let me see if him can do it. 24 amperes. First thing, Mr. Hope. Or what bad?
I'm still here, sir. I'm still here.
And 24 amperes. That's the input. What do we do?
24 divided by 8, we get 3, sir.
Good. And then?
Are you still using the time domain 1?
We never change it.
Okay, so if you draw a vertical line up where it intersects a 1, So the operating time would be like 0.8 seconds.
Beautiful. You see how easy it is? And if we were to use time dial setting 0.5, it would be?
About
4.3.
4.3.
About 0.3.
4.3.
It's right down here. 0.5, I said.
Yeah. Oh, 0.5.
Yeah. All right.
About
So
0.3.
at 120, come, give me another volunteer. There's nobody volunteer. Mr. Edwards.
Yes, sir.
Front and center. At 120.
You divide by 8 and you get 15, sir.
Okay.
And
So we get 15. So where are we? We are all the way up. Where are we? All right here. Right?
yes, sir.
Mm-hmm. So what time are we getting there now?
0.2. Is that 0.2?
It's a little, well, it's difficult to see from where you are, but it's about 0.15. The other thing about this, students, is that I don't want to tell me, look at something like that and tell me 0.18. I'm going to mark it wrong. You can't estimate with that level of accuracy, all right? So something like this, I would expect 0.1, 0.15, 0.2, but obviously it's less than 0.2. But you get the picture, Mr. Edward. This, oh Jesus. Yeah, Abhishek. That's what I remember. Yes, Mr. David.
In terms of the graph, for the ones that they don't go directly up. For example, we're looking at the one for was the first one, and I see where it does not intersect for the 0. Was it the 0.25? I think I don't remember the exact.
1.25. 1.25. Yeah.
For that, where we don't see it intersect, and like where we would see the curve cut, we just assume that it continues going up.
Which is what I'm saying. You would simply say that it is greater than the values that are here. So you'd say it would operate beyond 7 seconds.
Okay, thanks, sir.
You couldn't give a value. All right.
Yes, sir. I was about to ask the same thing.
So it would continue to creep with time, but it will be very slow, but ultimately it will operate. All right, so all right, we have 3 minutes. So I think we can look at that one. So write this down quickly. While you do that, let me see if I have everybody here. Okay. All right. We have a full class today. Okay, cool. So we have this network, yes, and this is how you would go about so I'm just going to do the first step in terms of relay operation or relay setting, all right? So we're going to go through the first step, and then we'll spend about 15 minutes next week. Next week is our last class, no? You know what I'm saying? Or is it a week after? Anyway, we'll figure it out. All right, do we have this?
So finish right it off. Give me a sec.
So, students, you have this system. You have an overcurrent relay. This is the maximum load. All right? It means, therefore, that you cannot select a tap that will cause the relay to operate on your maximum load. Is that clear? Because what that will mean is that if you load the system, yes, if the maximum load is passing through the system, then the relay is going to shut it down. But you know, you don't want that to happen. You want to be able to carry your maximum load at all times. So in terms of the steps, I'm just going to go through step 1, then we'll come back and we'll wrap it next week. All right, and we take it from there. So we're going to select a CT ratio that will not result in relay operation for the maximum load. All right? We can't allow that because you want your load to operate. Makes no sense to. And given the available taps, so we're not going to look at our CT. Good. And the available taps that we had on the CT, we had 100 to 5, we had 200 to 5, etc., etc. Remember those? So we're going to select a tap ratio of 20. Now, if I select a tap ratio of 20, what that means is that I would have, for the maximum load, a secondary current of 4.5, because the maximum load is 90, yes? And the CT ratio is 20. So I'd have 90 over 20 or 4.5. Everybody with me? If you're not with me, say it no, or forever hold your peace.
I'm not with you, sir, but I'll watch the video.
You're in and out, man. You're in and out.
Yes, I was saying I am not with you, but I will watch the video.
Okay. All right. So, based on the maximum current, maximum load, the output of the CT would be 4.5 because 90 amperes and we have a CT ratio of 100 to 5. So 100 over 5 is equal to X over, is equal to 90 over X. And from that you find X, it should be 4.5. Good? Now I want you to go back to the relay. All right? Now for this relay, I want you to tell me, and this is where we're going to end for today. Tell me what tap setting you would select for this, based on what we just calculated. Which tap setting would you select? Come on, man. You don't want to go.
Five.
Hi, Mr. Watson. Why would you select 5?
You really don't have any 4.5 there, so you don't want to select a value that's a little higher rather than lower than the original.
Well, let me hear. Watson, why did you say 5?
Well, so the reason I said 5, sir, because it's greater than the 4.5.
Now, Mr. Hope, you said you were looking for 4.5. But if you set it at 4.5, what will happen? Hope?
I don't think I'll be able to set that.
You said you didn't see 4.5, so you select something higher. And I'm asking, if you had found 4.5, would you select it?
Yes, sir.
Okay. So, Mr. Freighter,
Yes, sir.
tell him why that would not be possible. Why that would be a wrong move. Come on, Mr. Freighter, man. Depending on you.
I'm just trying to see if I follow Mr. Whoop. You're saying that if he sees 4.5.
Oh, so you weren't following the discussion. Okay, Mr. Duncan.
I was following, but I lost track of his response.
He said he would select the 4.5, and I'm asking you to tell him why it's wrong.
Yes, sir. If you use 4.5, that would be the maximum current. So you don't want the relay to operate when the load is at its maximum current.
And I said that about current. And Mr. Duncan, I said that about 4 times, didn't I?
Yes, sir.
All right, Mr. Whoop, you cannot select your tap to correspond with your load, your maximum load, because the relay is going to operate on maximum load. You don't want that. You want to be able to carry your load. So the selection would be 5. And we will stop it there for this evening. I think your appetite is wet enough. And for those who may have access to the video, they can watch it and hopefully update themselves. All right? I don't know anybody named Tracer, so you can put on your hand. All right? Well, that's it for me, you know. That's it for today's class. If you...
That's what you mean by that. All right, I cannot just get something else, sir.
What up, Mr. Whoop?
Even though you said it, I was looking at the wrong figure, but what you just explained, I understand it fully now, sir. Why you only select 4 points.
Excellent. And that is my purpose. If you don't understand it, then I have not thought. Yes, Mr. Morrison.
Good afternoon. Yes, evening. Good
Evening.
sir.
Yeah.
Sir, not jumping the gun, but would it be possible? Maybe this is not the forum to ask. Would it be possible, like at the last class, you can provide like a module outline for power system protection? I'm thinking of doing it next year, sir, but I want to brace myself over the holidays.
Oh, so you want to yourself over Christmas. All right.